on number systems. In the previous video, we learned the decimal expansion of rational and irrational numbers. In this session, we will learn how to represent rational and irrational numbers on the number line. So let's start. Friends, can you tell the type of expansion of the decimal number 2.8? This is a terminating decimal. Let's represent this number on the number line. The number 2.8 will lie between the numbers 2 and 3. Now we will divide the portion between numbers 2 and 3 into 10 equal parts like this. Friends, why 10 equal parts? Because this will make the process of locating the number easy. Here, the first number is 2.1, the second is 2.2, and in this way, the last number 2.9. And the number 2.8 will be located here only. Let's take one more example. Represent the number 4.233 on a number line. This is a non-terminating recurring number. How will we represent this on the number line? Let's see. Friends, this number will lie between the numbers 4 and 5. This is a large range, so locating the number at the right position would be difficult. So let us divide this range into 10 equal parts. Now this number would lie between the numbers 4.2 and 4.3. Friends, are we now able to locate this number accurately on the number line? We have just reached the first place after the decimal, and here, in this number 3 is getting repeated. Let's further divide this length into 10 equal parts. Now we can say that the given number will lie between the numbers 4.23 and 4.24. Friends, to get more accurate visualization of the representation, we will further divide the range 4.23 and 4.24 into 10 equal parts. So the given number lies between 4.233 and 4.234. If we notice the process, as we are moving ahead and dividing the parts, we are getting closer to the given numbers. Here we can say that, though we cannot accurately locate the given number on the number line, we can still represent its closest value. So, representing any number on the number line depends on how many numbers after the decimals are to be considered while representing them. To accurately or precisely locate the number on the number line, we had to divide or magnify the number line into many such 10 equal parts. So this process is called as successive magnification. Friends, so far we saw how to represent rational numbers on the number line. But can irrational numbers also be represented on the number line? We know that the decimal forms of irrational numbers are non-terminating or non-recurring. So, will we use the same process of successive magnification to represent them on the number line? Yes. Let's take an example. Represent this irrational number 4.810024500611 on the number line. This number will lie on the number line somewhere between 4.81 and 4.82. Friends, here the numbers are non-terminating and non-repeating after the decimal. Hence, even here, we will not be able to precisely spot the number, but we can still come to its closest point. Friends, we will be able to represent irrational numbers on the number line without knowing their decimal expansion. Yes, there is a way of representing these numbers on the number line. Let's look at it. Let's represent root 2 on a number line. How do we get root 2? When do we get any number in the form of roots? When any number is in the form of squares like x square is equal to 2, then we get x as root 2. Friends, when we use words like squares, square roots, which rule comes to your mind? Yes, Pythagoras rule. Now, if we consider a right-angled triangle ABC where the lengths of AB and AC are 1 unit, according to Pythagoras' rule, we will get the length of AC as root 2. We know that root of 1 is 1 and root of 4 is 2. That means root 2 will lie somewhere between 1 and 2 on the number line. Hence, if we have to represent root 2 on the number line, then we will have to construct triangle ABC in such a manner that point A will lie on 0 and point B will lie on number 1 on the number line. We will draw a perpendicular from point B of 1 unit length. So we get the length of AC as root 2. Measure the length of AC using a compass and draw an arc on the number line which cuts the number line at point E. Point E in the number line will represent the number root 2. Friends, that is it for today. In this session, we learnt about representing rational and irrational numbers on the number line. See you in our next session where we will solve some more questions and discuss this further. Thank you. In the previous video, we learned how to represent rational and irrational numbers on a number line. Today, we will be solving some questions based on it. Let's start with our first question. Represent the following numbers on the number line. The first number is minus 6.421. This is a terminating decimal. Friends, don't get confused seeing the negative sign. This number will lie between minus 6 and minus 7 on the number line. We will represent this number using the process of successive magnification like this. Now the number will lie between minus 6.42 and minus 6.43. Here. Friends, the second number is 8.34 bar. And according to the question, we have to represent it up to 4 decimals on the number line. This is a non-terminating recurring decimal. Will we be using the same process of successive magnification here? Yes. Please try to solve this question on your own. This number will lie between 8.3434 and 8.3435 on the number line. Now let's take another question. Can you represent root 3 and root 5 on the number line? In our previous video, we learned how to represent root 2 on a number line. Following the same method, let's see how to represent root 3 and root 5 on the number line. Here, point E represents root 2. We will now construct a perpendicular on line AC. Now measure the distance of 1 unit using a compass and draw an arc from point C on the perpendicular which cuts it at point F. Now draw a line joining center point A and point F. Friends, if you look carefully, here we are getting a right-angled triangle ACF. Here length of AC is root 2 and that of CF is 1. Using Pythagoras' theorem, we can find the length of AF which will be root 3. Now measure the length AF using a compass and taking center as point A. Draw an arc on the number line which cuts it at point G, and this point G represents root 3. Friends, we can represent root 4 using the same process. And now we get the arc cutting at point 2. This is because the value of root 4 is 2. Now to represent root 5 on the number line, we will draw a perpendicular on the line AH and measure a distance of 1 unit using a compass and draw an arc on the perpendicular which cuts at point J. Now, draw a line joining point A and J. We get a right-angled triangle AHJ. In triangle AHJ using Pythagoras' theorem, we will get AJ as root 5. Measure the length AJ using a compass and keeping A as center, draw an arc on the number line which cuts it at point K. point K represents root 5 on the number line. The formation obtained as a result of this process is called the square root spiral. Friends, till now we represented numbers which were in the form of root n, where n is a positive integer. But can we represent root a, where a is a positive real number on the number line? Yes, we can. Let's take an example for the same. Represent root 4.5 on the number line. Let's see how to do the same. On a line, take point A and B such that the distance between points A and B is 4.5 units. Now, from point B at a distance of 1 unit, mark a point C on the number line. Now find the midpoint of line AC, which will be AB plus BC divided by 2. Here we get O. Now taking O as the center, draw a semicircle using a compass. Draw a perpendicular from line AC at point B, which would cut the semicircle at point D. On joining O and D, we will get a right-angled triangle OBD. We know the length of AB is 4.5 and OA is 2.75. We will get OB as 1.75. In triangle OBD, on applying the Pythagoras theorem, we can find the length of BD. We will get BD as root 4.5. To represent this on the number line, we consider point B as 0 and point C as 1, and by taking the radius as BD, we will draw an arc on the number line like this. This point on the number line will represent root 4.5. In this way, we can represent any positive real number on the number line. That is it for today. In this video, we solved a few problems related to the representation of rational and irrational numbers on the number line. We will meet you in our next video with some facts related to this. Thank you. Number systems. Today we will discuss some facts related to the representation of rational and irrational numbers on the number line. Friends, we know that the collection of rational and irrational numbers together form real numbers. So if I ask you to think of any number, friends, I cannot predict if the number chosen by you is a natural number, an integer, or a decimal number. But I can surely say that the number you thought of would be a real number. This means that any random number that we can think of will always be a real number, and we can represent all the real numbers on the number line. So friends, tell me whether this point on the number line represents any particular number. Yes, we cannot say whether this point represents a rational or an irrational number, but it definitely will represent a real number. And all such points on this number line would represent a unique number. Let's move ahead. The points 4.3 and 4.3 bar represent the same point on the number line. Is this statement correct? To find the answer to this question, you may pause the video. Friends, both these numbers are rational numbers, but 4.3 is the terminating decimal. We can accurately represent this number on the number line this way. But 4.3 bar is a non-terminating decimal. Here, the number 3 is repeating itself after the decimal. This number will lie on the number line between 4.3 and 4.4. That means the numbers represent two different points on the number line. Hence, the given statement is wrong. Friends, That is it for today. In this session, we discussed some facts related to representation of rational and irrational numbers on the number line. Let's meet in the next video. Thank you.